Hi, can you hear me?
Yes, I can hear you. Hello. Can you hear me?
All right, yeah, I can hear you well. Let's get
Great.
started. Right.
Sounds good.
Okay, so we'll jump right into the question.
hmm
We are going to have an interview on coding and problem solving, right?
Yes.
Yeah, that's the expectation. Okay. So I'm going to ask you a very simple question, and I'd encourage you to ask me follow-up questions to disambiguate the problem and also lay out any assumptions that you're making. Don't
hmm
jump to problem solving directly or writing the code. I would encourage you to also discuss the problem with me, the approach, how you're thinking about the problem, and eventually, once we agree, we can start thinking about the code and then writing the code. As part of this interview,
Sure.
I'd expect you to disambiguate, like do all these things, discuss these things with me, and then eventually also produce the working code for the problem that I'm going to ask you. All right?
Great. That sounds good.
All right, great. And so the problem I wanted to ask you was, suppose that you have a linked list and you need
hmm
to delete a specific node from the back of the list, right? So
Okay.
suppose you have a linked list containing 10 nodes, and you would be given this linked list, and you would be also given something like you need to delete the kth node from the back, which may be 5, or which may be something like 3, or which may be the very last node. So this is what you
hmm
need to do. You need to have the node deleted from the end of the linked list, that position of the linked list, and then return, and then return the linked list back to the client.
Gotcha. Okay. Okay. Sounds good. So to clarify, can I just write an example here? So if it was like, can you see this here on the message?
Yeah, yeah,
Yeah. Yeah. So if k was like k equal to one, then we'd want to return the list like that, right?
yep,
Or
exactly.
sorry, if it was k was two, maybe k was two, like second from the end, I guess, but some number, right? Okay.
Yes, yes, yes.
Um, okay. Are there and then by returning the list, we'd return the head, the same head, right? That
Yep, exactly.
yeah. Okay. Okay. Are there cycles in the list?
There,
Like,
y-
I guess that
y-
wouldn't make sense because then it
yeah,
couldn't be k from the end, right?
exactly. That's a very good question.
Okay.
Let's assume that there are
Yeah.
no cycles in the list.
Okay. No cycles. Um. Okay. And will k always be greater than k be less than the length of the list?
It might be.
It might be, but it could also be greater than.
Yep.
Okay. Um, let's see here. Can the head node be null?
Yep.
Like the pointer? Okay. Okay. Let's see, is there anything else here? Um, yeah, I don't know. I don't think there's any other questions I have. I think that's pretty clear. Wow, what's the length of the list, roughly? It can be like quite long, right?
Yeah, it can be. So, what do you mean by quite long? Like, what is the
Hmm.
thing that you're getting at?
Oh, just like what's the length of what's basically trying to figure out the upper bound of the input, the length of the list essentially. But I guess it can be really, really large if necessary, right? So
It can be really, really large if necessary. So, I want to
okay.
understand
Yep.
what you mean by really, really large.
Oh, I don't know, like millions, billions of items in the list or something. I mean, maybe is it something that can it fit in memory? Is it all going to fit in memory? Um,
Okay.
yeah.
Let's assume, yeah, that's a good question. Let's assume that for now, it can be large, but not that large that it won't fit in the memory. So it
Okay.
will fit in memory basically.
Okay. Okay. Sounds good. Cool. Yeah. Okay. That sounds good. I think. Yeah. Is there anything else I might miss that may be critical in terms of the constraints of this input? I know I'm supposed to
Uh,
prod and find them, but this is kind of
no, I think this is pretty exhaustive.
okay. Okay, that sounds good. Um, shall we now go into kind of maybe my first pass of the approach, or we're good here?
Yeah,
I can kind of talk to you about
definitely.
it, not code it, but yeah, okay. Okay. So naively, the thing that I think can be done is in one pass. Well, okay, so to get the K from the end, totally naive here. Iterate over the entire list to figure out how many items are in the list, and then
Okay.
uh, super naive, super dumb, but like I iterated over again up until n minus k, and then you just perform the operation to strip that out from the linked list and return the head again. So it's like a O of n and O of one, O of n time, and then O of one space. Um, yeah, that's the super
Okay.
naive version. Um, we can improve, I suppose. I don't think we can do any better
Uh,
than O of n, but I think,
yeah.
yeah, yeah,
Yeah, I think
maybe
in
like
terms of
constant factor less, right?
yeah, exactly. Something like where you don't like reiterate over the linked list more than once, or don't reiterate
Yeah,
basically.
okay,
You traverse the linked list once.
yeah, okay. And is this something that we can expect to do with constant memory, or is it acceptable to have like up to k O of k memory?
Let's talk about both the approaches.
Sorry, can you repeat that? I
Yeah,
misunderstood you.
let's explore both the approaches.
Both approaches.
Like
Okay.
if you
Um,
have any in
yeah,
mind, let's talk about that. Yeah.
sure. Okay, so another naive one. Not naive, but you could just walk down the list and maintain k pointer like I suppose like a queue of the last k nodes you've seen. Um, double-ended
Okay.
queue. As you see them, you add it to the end, and if the queue length exceeds k, you pop off the leftmost, frontmost element, and that way you kind of keep this window of either last k elements. Um, yeah, and then once you reach the end of the node, once you reach the end of the list, uh, if assuming that k is less than the number of elements you've seen, which makes it valid, then you can take that element at the front of the queue. Since you have a reference to it, you can actually you need k plus one because you need to have the previous pointer, and then you can strip it out from the list and just return the head.
Okay.
So that's a way to do it O of k.
Okay, just one clarifying
Mm-hmm.
clarification. That would be
Yeah.
that you need to delete the kth element from the back. So what you described to me would delete the kth element from the front, right? Or did you
No,
mean
yeah, I meant
so?
so. For example, up here, if we were doing,
Yeah,
yeah, I can show you kind of an example. So if I run through it, it'd be like, so for this top one, like 1, 2, 3, 4, 5 here, right? So by the time you reach the end of the once you reach the
right.
fifth element, this is what the queue would look like. And
Exactly.
so yeah, yeah. So it would be second from the end, and then you take the parent pointer of the one you want to strip out, which is the first element, and then you would reassign to that element to point to the k to the element adjacent after after this
Okay.
one,
So then
and
it
then you
becomes
would return this
two,
whole list.
two and
Yeah,
five. But how do
exactly. It would
you?
become like that.
Okay, but then it becomes two and five. But how do you plug it onto the next of one?
Oh well, you just maintain a pointer to one at the beginning. You just maintain a pointer to the head, because like it would. Oh, did you want this to be done? Sorry, maybe a clarifying question is, can we do we want to modify this in place, or do we want to generate a new list?
I think, yeah, what you're describing is modifying it, not in place, generating a new list, but okay.
Well, no,
And
I'm talking about, no. Oh, sorry. Yeah, the approach I'm describing, sorry, is to keep it to modify it in place. So this queue is just for reference, just for references to the input list, if that makes sense, right? So it's not, this is not going to be the return list or anything. What I'll do at the very beginning is maintain a pointer to the head of the list, and then
okay.
return that at the very end after performing the surgery to remove this to remove that kth element. So yeah, it'd be in
Okay.
place. Yeah.
All right. Let's go over this approach once again. So, how do you come? So, how do you determine this? It would be a three length list. Can you maybe show me with explain with another example? Let's say you this list is longer, something like
Yep. Let me add some elements here.
concept.
I guess
Yeah.
the numbers don't really matter. Yeah. Well, I'll keep them unique here just for the sake of whatever. 11. And then let's say like 13, something like that. And
Yeah.
k is equal
Suppose
to specified
three. Let's go with three.
3. Okay.
Yeah.
Okay,
Okay.
cool. So at the very beginning, what I would do is maintain a head pointer
Okay.
reference, which would just equal 1. So it's just kind of like keeping a reference to the first
All right.
one. This is naive.
All right.
There's some edge cases here, but this is kind of the rough idea. And then
Okay.
we maintain some kind of queue here, right? And
Okay.
so, we go to the first node, add it. And then if we go to
Okay.
the second node, we add
Okay.
it. And we keep going until the queue becomes k plus 1 equals max length of this, is basically what this is, if that makes sense, right? And then
Okay.
once we visit the 9, what ends up happening is this becomes 9, and then we pop off the first one. So it becomes like that. And we proceed until we get to 13, 11, 9, and this would be at the very end here. Once we've reached the end of the list, this is what the queue would end up looking like.
Okay. So
Does that make sense?
essentially, you are keeping a kind of a double-ended queue, and
Yeah.
all right.
Yeah.
Okay.
But I think
Now
that's
you have,
unnecessary. Sorry, I know we're spending a lot of time on this. Oh, sorry. Yeah.
yeah, that's fine. So now you have 5, 9, 11, and 13. What do you do next?
What I do next is I will take, so once we've reached the end, we so this 5 here is a pointer to this 5 in this list. So I'll revisit this here. So we take the first element in this queue and we reassign it to this second element. Oh, sorry, the third element, which is the element after this is k here. So 9 is k. So we would essentially update the linked list to look like this, and then we return head pointer, which is equal to 1, and which is the
All,
beginning of the list, and that'd be it.
all right. All right. Got it. Yeah.
Yeah.
Now I understand it completely. And over here, what would be the time? What would be the space complexity?
Yeah, time complexity should still be O of n because the queue operations are O of 1, both sides on the double-ended queue.
Okay.
Space is O of k. Yeah, space should be O of k
Oh,
though. Yeah. Oh, and sorry, the linked list removal process is just reassigning pointers, so that's constant
yeah.
time. That'd be O of 1. Sorry, to make that clear. Yeah. So overall time would be O of n, but with one pass essentially, in a sense, and
Okay.
but O of k memory, which I think is not optimal. I'm pretty sure there's a way you could do this with O of 1 time. Oh, sorry,
All
space.
right. Yeah. Yeah. So what is the okay? So do you have a O of 1 approach in mind with space?
Yeah. Yeah. I'm guessing you could just uh I mean,
So
once you've
going,
performed
yeah.
k iterations, yeah, once you've
Yes.
performed k iterations, you get out to like, so k of 3, let's say we're out at 5.
Exactly.
Once you've reached that point, you can start having a second pointer follow. So it
Exactly.
becomes like Yeah, yeah, I think that'd be the more efficient way to do it, and that becomes O of one memory. So this example here
Exactly.
would be like, yeah, first pointer. I think you get it. Should I just code it
Yeah,
for
yeah,
the sake of
definitely.
time?
Yeah.
Yeah, yeah, I think you understand, right? So yeah,
One of
is
the
that
assumptions,
sufficiently?
and I think one of the other assumptions that
So,
we made for this question was that it's a singly linked list. If it had been a doubly linked list, then it would have been easier. But yeah, I think we started off with the assumption that it's a singly linked list.
ah,
So yeah, that's fine.
yeah, yeah, yeah. So, oh yeah, I should have asked that. That's a good question. Um,
Yeah, that's
yeah,
fine.
I don't
Yeah.
know. Okay, okay. Cool. So I think that makes sense then. So kind of like a two-pointer runner system, right?
Yeah.
Um, yeah. Does that work? Shall I code that? Would you
Definitely,
like me to
definitely.
clarify the solution a bit more? Or
No, I think I got the solution. It's essentially the same solution as the queue-based approach, just that you are not keeping the elements in the middle of the queue. It's just the head and the tail of your queue that you're
yeah,
maintaining. Yeah.
yeah, exactly. Yeah.
Yeah.
Okay, cool. That sounds good. Um, nice. Should I code it? Changing the
Yes.
language, changing the, yeah,
Yeah. Whatever you're
that's
comfortable
okay.
with.
Okay, sounds good. Okay. Do you have a function signature I can use, or is there,
You can come up with your own.
okay, sounds good. So we're calling this remove K, case.
And I would also want you to
Uh,
handle the different edge cases. So keep that in
yep.
mind.
Yes. Yes. Yeah. I'm gonna get the meat of the algorithm down if you don't mind, and then I'll kind of
Sure.
approach the edge cases as we go. Yeah, like where k is greater than the length of the list and such and stuff like that. So, um,
Okay.
yeah, let's do that. Okay, so our input's gonna be head of list and k.
All right.
Okay, basically, right? Yeah. And this is gonna be.
All
Let's
right.
assume we have some optional node, and this is an int. I guess this is a uint. Well, there's no uint in Python, but and then we're returning a optional. Oops, sorry, optional uh, node, and then
Mm.
node will be just and then it's got val. Well, it has a value. It has a next basically.
Yeah.
Yeah, that's fair. Okay, we're good.
Yep.
Same page here. Okay, cool. Sounds good. Okay, so what are we gonna do? High level steps here. Um, high level, we are going to run. So we have 2 pointers. Um, okay, emit 2 pointers. Maintain reference to head of list. Probably with, oops, sorry, with dummy header important for edge case for later. I
Okay.
think when yeah, because we're gonna, it's possible that the head is the one you have to remove, right? So got to think about that later. Um, okay, so the meat of this loop is here. Let me think about this. So we're gonna run out one list. What's the termination case here? So pointer, essentially it's gonna be something like here. While pointer two, I'll say first pointer, while it exists, what we're going to want to do is reassign to next pointer. Oh, reassign to next, but also update following pointer. What's the condition when we update the following pointer to the next? When count we've processed k+1 nodes, I think. This is edge case. I'm not sure if it's k or k+1, but we have to keep a reference to the previous node.
Yeah.
Yeah, right? And then we assign first pointer. I'll call it lead pointer.
Yeah.
Yeah, lead pointer to next. Okay. And then after we've done that, now here at this point, we have a reference to the presumably parent node of the one we got to remove. So we want to remove the next node of the following pointer
Okay.
from linked list. That's kind of the rough idea, and then return the head of the list. Toss next of dummy head. I think that's the rough algorithm. Hopefully that makes sense.
Okay.
Does that kind of make sense? Yeah. Anything odd here?
No, I think it's more about the edge cases, but overall the approach I think looks fine.
Okay, sounds good. Okay, so let's go lead pointer equals head following pointer equals head dummy head equals what do we want to do here? Maybe node, just empty node.
Okay.
We can sort this out. Dummy head dot next equals head for now. Okay. Yeah, okay. And then we need a count. Process. I would say count. So for sure at the end of this loop, we got to increment the count. That's one thing we got to do. We also want to check the count. We also want to reassign. So lead pointer dot next equals, lead pointer equals lead pointer dot next. And then here we also want to check if count is greater than or equal to, say greater than k. We'll come back to this. This is edge case here. Edge case. I'll talk about it later, but roughly, yeah, if count is greater than k, then we want to increment the following pointer equals dot next. So yeah, okay, so this should walk down the list, and eventually lead pointer will hit the case where there's nothing. This loop will terminate. Ideally, barring edge cases, the following pointer is going to be pointing to the its child will be the case element from the list. Hopefully, I'll think about edge cases in a bit, but yeah. And then here, let's say node. Or maybe just do it in line. It's fine. Okay, so here we want to remove. Let me see. Following pointer dot next. No wait. Yeah, maybe something like that. Handle this up here, and then return dummy head dot next. Okay, something like that. Now removing this node. Okay, so we're going to take this. We need to keep a let's see, node dot next dot node dot next dot. Naively, this is what we need to do. Now it's possible that edge case possible next dot next or next is null, right? So I think in the case that it's not, is this sufficient? I think it is, right? To remove it.
Remove next
Because
and remove the node dot next. Do you need to deallocate some memory? or
I don't think in Python it's necessary, but if I was using some memory managed language, it would be, I think, necessary to deallocate the memory. But I
okay,
think Python is
it
yeah,
will
it's
be garbage.
automatically memory managed. So yeah, it'd be garbage collected, or yeah, I don't think it's reference counted, so I think it's garbage collected. Um, but yeah, but I do need to check if the next one doesn't exist, right? So if
Exactly. Exactly.
yeah, if not node.next, node.next equals none, basically. It just point nothing to nothing. Yeah. Otherwise, else, I think it's like that. So if the node next does not exist, yeah. And then we also have to make sure if following
So
pointer,
if node
sorry, go
next
ahead.
does not, yeah. So if node next does not exist, what kind of a scenario, like what kind of an input would give rise to such a scenario?
Good question. That would be if k is equal to 0. Would that be 0 from the end? Meaning,
Hmm.
yeah.
So in that
So
case, do you want to iterate over the entire list and then find this out, or you want to basically preempt the computation?
you could preempt it for sure. That would be, yes. That would be somewhat of an, not edge case, but I guess it's somewhat of an edge case. But that is a good point. I suppose then, yeah, this would not be necessary. Um,
Yeah. But you can still
especially,
keep it because
yeah, it's safe.
someone else
It's
might use
safe.
the function. But yeah.
Yeah, yeah,
Okay.
that's a good point. We can add that up here. So it basically preempt everything here. Like, yeah, essentially, if an edge case is if k is equal to, oh, we don't know the length of the list at this point though. So, but yeah, actually, the thing is, we don't know the length of the list, right? So we'd have to iterate over the whole list anyway. There's no way if we knew the length of the list, then we could compare it to k at
So
the beginning, right?
it gives you k is the position of the node from the back of the list, right? So if k
Oh,
is
yes, of course. Sorry. Yeah, I understand that. Yeah. So if k is equal to 0, return head, essentially. That'd be one edge case.
okay,
Yeah, yeah,
yeah.
sorry, yeah. Yeah. So remove next. Okay. Um, okay. So let me walk through this. So there's a possible case where following pointer is null. Is that possible? Yeah, I think that's okay.
Where
No, there's
following is null. How can that be a case?
um. Let's say k is equal to the length of the list.
Okay.
Then I think one thing I'd have to do is check. So yeah, okay. Here's an edge case here. If count is equal is if k is greater than or equal to count,
Hmm.
right? Then actually, so because following pointer is head, um, I need to exit out early here because that would be kind of an invalid case here.
Hmm.
We wouldn't want to remove the head, right? So let me I'll think
Oh,
about this more clearly with an example.
why would you
Sorry,
not
what's
want to
that?
remove why would you not want to remove the head? Suppose you have something like three element list, one, two, three. The nodes
Yep,
are one, then two, and then three, and you
yep.
have k equals to three. So in that case, you return two, three, right?
Oh, I actually thought if k was 0, oh,
K is three. K is three.
first element from the end. Yeah, okay, that makes sense. Okay, yeah, so it'd be if k is strictly greater than count.
Yeah.
Yeah, and then that would mean that this would have to actually start with dummy head because it needs to point. It has to be the parent of the node to be
Yeah.
removed,
Yeah.
right? I think that makes sense. Yeah, yeah, that's a good point though. Thank you. I appreciate that.
Yeah.
If k is strictly greater than, we got to return. What's the desired behavior if k is greater than just return the old head?
K is no, I mean ideally, how would you deal with it? Like if you're calling an API and if you have some invalid input, then what would you typically
It
expect in a production environment?
yeah, it'd be to throw an exception or raise an error or something.
Yeah, yeah, let's
Yeah.
do that. Let's try
Yeah,
exception. Yeah.
yeah, throw exception here and then you know, K greater than length of list. Yeah, something like that. Yeah, it's kind of something like that. Okay, how are we doing for time here? We got 15 minutes or so.
Yeah.
Okay, let me run through it with an example to kind of nail down some of the edge cases here. Or let me write some test cases and we can kind of go through them. I think the meat of the algorithm is here. Is there anything missing aside from edge cases? I think it's okay,
No,
right?
edge cases are only remaining. There are a couple more edge cases, I think,
Yeah,
but everything's
yeah.
fine.
Okay, sounds good. Let me process it up here. Um, okay, so let me think of some edge case test cases here. Okay, so null, one element. Yeah, no, I'll just represent it as a list here. I mean, one or two, that could be a weird case and this would be with k equal to, say 0 or even k equal to 1. All these boundary cases, k equal to 2. In this
Okay.
case, okay, so if not head, right away we can handle this one. If not head, return head, return like none, doesn't matter, right? So we can just, yeah, that handles that case. Okay, so we'll go through all these boundary cases. Let's see what else we can handle here. So with 2 pointers, well, 0, we already handled that, so we don't have to worry about that. But the ones we care about are around the boundaries of, say, 1. Oh, hello?
Yeah, yeah. Go on, go on. I'm here. Listening.
Oh, sorry, sorry. Okay, sorry. I think I accidentally
Hmm.
went to the whiteboard. I was like, I got teleported. Okay,
No,
2, 3.
fine.
Try those cases. And then I think this, yeah, okay. If I have time, I'll go for the rest, but let's go through these. Okay, so if we're with one element, so lead pointer becomes 1. Dummy head is null, not null, but it's a node, essentially null. And then dummy head is now equal to, oh, it's also equal to 1. Oh, next. Okay, I see. That's different. Okay, which points to 1. Following pointer was going to be none pointing to 1. Basically none. Count 0. Okay. So what will happen here if count of k, it's not count is 0, k is equal to, oh yeah, and assuming, sorry, k here in this example, k is equal to 1. So 0 is not greater than k, so we don't follow in this here. Lead pointer next, so lead pointer now becomes none, and count is now equal to, yeah, so lead pointers next is equal to, yeah, so this is not right. This is already an edge case that's failed.
Yeah.
Yeah, so we got to start actually with head, I guess, is equal to, maybe, I wonder if this makes sense. Oh, actually, let me just think about it. Okay, so if we point it at 1, instead of just wildly here. Okay, so if the pointer is pointed at something in front of it, it iterates once, it goes to 1, count now becomes, count is 1, and then it's still valid, and the next iteration if k is greater Actually, you know what? This is okay. This is okay if it's empty, because what happens is sorry, let me back it up to what it was before. So it starts at head. So following pointer is pointing at the dummy head. We end this execution. Count is 1. We exit out. K is 1. K greater than count, not true. K and 1 is equal 1 and 1, so we don't throw an exception. Then we remove the next of the following pointer, which is the dummy head's next, which is actually the head, which is 1, right? So now we end up, so dummy head. Now okay. The edge case here is where, so the edge case here is if the following pointer is equal to the dummy head, then we remove the first node and we need to update the dummy heads.
Exactly.
Pointers. Dummy head. Return none, basically. I think that makes sense.
Yep.
So return none there. Okay, so that handles the case. Yep.
Yeah. Do you think
Sorry,
there's any emphasis missing, or have you covered everything?
Sorry, what?
Yeah, I'm asking. Do you think there's anything missing?
Edge cases. I don't know for sure. I kind of wanted to run through one more, but
Sure.
I think it's on. Yeah, just in case here. Yeah.
I think the fact that K might be negative because you can't have unsigned int over here. You might want to check that as well.
Yeah, it's true. Yeah, it's a good one too. Yeah. And the desired behavior is just or K. Well, I guess if K is less than or equal to 0, return head maybe. Oh, and actually, if K was negative, then it'd be a return an error, right?
Yeah, exactly.
Yeah. Exception, invalid, K. Something like that.
Yeah.
Okay. I think that's roughly it. I could run through some more cases, but I think this is pretty
good.
That's fine. I think it should cover. Okay.
Now let's try to discuss the approach if you are not able to fit this in memory. You don't need to code that one out, but I want to just talk about the approach.
Sure. Yeah, good question. Okay, so it's not in memory. So I suppose it's on disk somewhere in a database, these pointers or something, or maybe a graph database or something, right?
Yes.
Okay. I suppose what we could do, so naively, just loading in chunks, whatever will fit in memory at a time, and you could perform the same algorithm essentially, where there's just a delay, at this, so basically when you're looking for the next pointer, like here at this step, it's possible that at this step may be necessary to load next x. Oh, actually no, because you don't know what the next ones are. Well, maybe you could perform that query in the graph database. I don't know. Maybe this is something that could be.
Then you would go through the entire thing, right? Okay, let's assume that you just, if the next exists, let's assume you know that.
Let's assume that you know the next, but it's in okay.
Yeah, because every node you would get to see that whether the next is pointing to something or it's pointing to null, right?
Yeah, like if you create the database, if you create like a GraphDB or something.
Yeah.
But the problem is like the problem is though, like doing it, like having this have to do a network hop for every call is too slow. Like that just doesn't make sense to do. So you'd have to kind of like almost load in chunks at a time, or query the GraphDB in a particular way where you set like limits on how far it travels, or like how many iterations it tries to go. Maybe that makes sense. Does that make sense or no?
Yeah, that does make sense. So let's say there's a way by which you can uh, actually pull in chunks. Let's say there's something like that.
Yeah.
So there's an
Okay.
API which is basically managed by, like in a GraphDB, even though you have a graph database, you still have the connections stored in a different place. So usually what it would be that there would be the next pointers, they are stored somewhere, and the entire body of the node is stored in some other place, and these are essentially the place where you have the connections. It essentially also has a pointer to the rest of the body of the node. So you can load multiple nodes at the same time if they're neighbors of each other.
If they're okay. Uh, Sorry, can you clarify that last little bit one more time really quickly? Sorry.
Yeah, so I'm
I
saying that
apologize. Yeah.
let's no, fine. Let's assume that there's a way by which you can load the next m elements, next m
Okay.
nodes in the link. Suppose you can load that in
Right.
memory. How would you do that?
Right. Okay. Gotcha. Yeah. Okay. Yeah. So basically, what I would do then here is, um, we at the beginning kind of load m elements or chunks,
Okay.
and then essentially decrement some counter, like have another counter that we track, which determines how far along those m elements we've traveled, or m nodes we've gone through. And then once
Okay.
we've well, let's say now we know there's no elements left in that chunk we've loaded, so we can fetch the next m elements, and we just continue through the same algorithm. But basically, it's batching. It's like batch loading from memory, and performing the same thing. Um, Now the challenge is when we've reached the end of the list,
Yeah.
does it make this following pointer? I think it still should have a reference. It can maintain a reference to whatever unique identifier that that element has. Okay, so we'd have to store two things. We'd have to store the following as well as its. Oh no, we could just keep the following pointer, whatever, like maybe an ID of whatever the row is for that entry in the graph database, right?
Okay.
And then we'd have to make maybe another query to get the next one, or we can store the IDs of both, or all three. I guess, yeah, because the round trips can be expensive. So what we'd want to ideally do is have enough stored on in the application layer in this code, where we can just make one call to the database to kind of update the 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 following pointers next, right, or whatever it points to next, with the ID of the of its next. Does that kind of make sense? So like remove node. Where's remove
What if
node?
the value of k is
Yeah.
more than m? Would that cause any problem in this approach?
If the
M
value
is,
of
yeah.
if oh okay, if m is, sorry, could you ask the question again? I kind of cut out there.
What is so m is the count of the number of nodes that you can load at a single time from your
Yes.
graph database into your memory, right? Now,
Right.
if the value of k is more than m,
Ah,
would that be a
I see.
problem?
Yes, I think that would. Um, yeah, that's a good point. It would be, since um, getting the getting the K, then yeah, it would be, because now you don't have K's next loaded in memory, right? So good
Yeah.
point. So I think what you'd want to do is maybe maintain a window around both if possible. So you'd iterate um up until count. You keep loading chunks of M until you reach where you've now run into you processed K nodes, if that makes sense. Then
Okay.
yeah, and
All right.
then
Yeah,
oh
I think it makes
yeah.
sense. Now, another thing to consider is, suppose not M is configurable. You have this unique database where you can configure M. So how would you determine
Hmm.
the size of how would you come up with the size of M?
Good question. Good question. Okay, how to come up with the size of M? Could maybe use, hmm, well, one, it definitely has to be less than the amount of, um, uh, well, you take a look at like how big the size of the individual like data entries are coming back, like in
Yeah.
the graph database, like whatever, yeah, a link, like whatever that size of chunk of data is for one node, and then figure out how much memory you have on a particular server or whatever, um,
Yeah.
server
Exactly.
size you're
So
using, right?
have
Yeah,
to
yeah.
disposal divided by the number of each node. Okay, uh, but are we maintaining two such blocks or one such block?
We would maintain two. So because we'd be keeping a window around both the K and the the lead and the following pointer, it'd have to be
Yeah.
like roughly server size divided by two for each window with some buffer because obviously you can't like have it like packed on that server.
Yeah.
Maybe give it a
Okay.
little bit of room, but yeah, more or less like server size divided by two for each window.
And you do server side divided by 2 by for each window. You do this divided by 2 only if k is such that you can't fit k nodes into the memory at the same time, right?
Yes, that would be correct. Whereas if you could, you can just maintain one window of size. I mean, the larger the M, the better, because you'll reduce your network trips. So you could have one big window and process it as you go. If K was less than
Yep.
M, in that case.
Yep.
Yeah,
All
yeah,
right. Yeah.
yeah.
I think that kind of sums up our approach. So yeah, I think we have also crossed our time. So it's supposed to be 45 minutes, right?
I think so. Yes, yeah, that's
Yeah.
correct.
Okay.
I'm assuming
All
so.
right. All right then. Do you have any questions for me?
Um, no, I don't think so. Um,
Okay.
yeah, these questions supposed to be like, um, well, actually, I guess this is a mock interview, so I should pretend like we're an interview. uh, um, no, I don't think so. Maybe out of curiosity, what would be another good follow-up question to this kind of question that you might ask other candidates, or you know, or is it, yeah, is like the
I
memory, like is the memory follow-up question one that is a typical follow-up, or
I mean, it depends on the level of the candidate, right? If the candidate has significant, it's not about the experience. It's basically for if the I'm interviewing the candidate for senior level or staff level, then I would expect this kind of thinking as well. But someone out just out of college or maybe after 1 or 2 years of experience, I would typically not expect them to think of a distributed structure for solving the problem. Another approach would be, well, it's not really relevant in this problem, but is
hmm
there any way by which you can, maybe I would try to tweak the problem and try to see that if on a single machine, can they employ concurrency to solve the problem faster? That might be another question.
mm, gotcha. Relevant to this question specifically, or is a general follow-up to any kind of question?
I mean, whenever there's any graph traversal questions or any traversal questions, then there are two ways. Like one is obviously if the data is so huge you can't fit it in memory, and the second one is
hmm
what you have multiple workers, and multiple workers are
Right,
essentially then you introduce some level of concurrency. If you can plug
right.
both of these, if your question is such that you can plug both of these two aspects together, then it might be also a question where your database is distributed and you are having
Mm,
workers on two different machines or n different machines and they are working concurrently.
mm,
How do you solve the problem? It's like a very big distributed cluster, say.
yeah,
So that can be another follow-up.
gotcha. Okay, okay. That makes sense. That's a good one. So like, yeah, I see. Concurrent on a single machine or distributed, like distributed processing for this, right? Yeah. Um,
Yes.
cool. Sorry, and are these questions I can ask you, like, is this um as if we were in the interview, or like just generally, as somebody who's conducted lots of interviews?
As in, I did not get the question. Sorry.
Oh, sorry. Is it okay if I ask you questions like just feedback really quick right now, like getting out of the mock interview phase? Or
I am not sure. I'm not sure actually whether we are allowed to do that. But yeah, I would.
okay, okay,
I think yeah, I'll just write it on your feedback. I'm supposed to. I have
okay,
prepared the notes anyway. But yeah, I
okay.
think
Gotcha,
overall it went pretty well. Yeah.
gotcha. Okay, okay,
Okay.
okay. Sounds
Yeah.
good. Um,
Yeah.
yeah, cool.
All right.
Yeah, I
Yeah.
don't think I have. Yeah,
All
no
right.
other
All right.
questions. That was great.
Cool.
Yeah, that was great. Thank you very much.
Yeah. Thank you. Bye bye.
Thank you. Take care.